What if I told you that the strongest, most resilient enterprise networks in the world are built on a foundation of completely invisible logic?
I mean, it sounds a bit like magic, but yeah, it's true.
Right. Today, we are throwing out the physical blueprints. Usually when you talk about building something massive, there's this expectation of absolute physical precision.
Oh, absolutely.
You pour the concrete foundation, you bolt the steel beams together, and the architect points at the structure and says, there it is. That's what holds the roof up.
Yeah, it's grounded in the physical world. I mean, you can walk up and literally touch a load-bearing wall.
Exactly.
But step into the world of modern enterprise network architecture, and that tangible reality it disappears.
Yep.
We're building these sprawling mission-critical structures out of, well, algorithms, virtualization, and software overlays.
And if you are joining us for this deep dive, that invisible landscape is exactly what you are preparing to master. Welcome to a highly targeted session designed just for you.
Glad to be here for it.
If you are listening, you are likely gearing up to conquer the key technical concepts and assessment objectives for the HPE7-A11 exam.
Which is a beast of an exam, by the way.
It really is. So let's look at the baseline parameters of the certification test. According to our sources, you are facing a proctored 2-hour English language exam. You've got 70 questions standing between you and certification, and you need a 66% to pass.
Right. Which means passive memorization is just not going to save you here.
No, definitely not.
The HPE7-A11 exam doesn't just check if you can, define an acronym. It tests whether you actually understand the deep architectural logic and the security mechanisms of Aruba solutions.
Really testing the why and the how.
Exactly. Picture a digital blueprint of a massive multi-site enterprise network right behind us. That is the environment we are learning to navigate and troubleshoot today.
And we have a very clear mission to get you there. We're going to tackle 10 specific practice questions.
10 of the best ones, yeah.
For every single one, I'm going to read the full text of the question stem aloud, exactly as you might encounter it on the test.
That's super helpful context.
Then, instead of just giving you the answer key, we're going to break down the problem-solving logic. We will analyze every single option A, B, C, and D to explain exactly why a technology fits the scenario, or, why it's a dangerous trap.
And there are plenty of traps.
Oh, for sure.
Yeah.
Okay, let's unpack this. We'll start where every network starts, at the edge, where users actually connect.
Yeah, the edge is where the design gets really tricky. I mean, you want robust control and security, but if you have, say, 50 remote branch offices, you absolutely do not want the physical footprint and power consumption of a server room in every single location.
Right, that would be a nightmare. Which brings us to our first scenario. Here's the question stem. A customer wants to deploy a wireless network across multiple branch offices using AOS-10. They require seamless roaming within each branch, but do not want to deploy physical controllers at the branches. What is the recommended architectural approach?
A very standard, yet strict design constraint. No physical controllers at the remote sites.
Let's parse the options. Option B suggests deploy virtual gateways at each branch to handle local data forwarding. Option C says, tunnel all branch traffic to a centralized gateway cluster in the main data center.
Okay, keep going.
And option D offers, utilize Mobility Master hardware to orchestrate routing across all remote locations. I'll be honest, B, C, and D all sound like they're trying to sneak some form of heavy infrastructure back into the mix.
They absolutely are. Let's break down the mechanisms here. Option D introduces Mobility Master hardware, which directly violates the explicit requirement of no physical controllers.
Right, it's just ignoring the prompt.
Exactly. Now, option C, tunneling everything back to a central data center, might sound clean, but it creates a massive bottleneck. If the wide area network link goes down, the branch loses all local switching capability. You basically sacrifice local survivability.
Which is bad.
Yeah.
And option B, the virtual gateways.
Well, virtual gateways still require a hypervisor like an ESXi server running at every single branch. You've just traded a physical hardware appliance for a server appliance.
You still have management overhead at every site.
Precisely. You haven't actually solved the problem.
So by process of elimination, we land on option A, deploy APs in bridge mode and utilize Aruba Central for management and policy enforcement, which is the correct answer.
It is indeed.
I like to think of bridge mode like a system of smart traffic lights. Those access points act as an intelligent intersection that can manage the local data traffic flow entirely on its own switching packets directly onto the local LAN.
I like that.
But the policy dictating how they behave is pushed down from a citywide cloud system, which is Aruba Central. You get full control without posting a physical traffic cop at every corner.
That's a great way to visualize it. It's a controllerless data plane with a cloud-managed control plane. It scales beautifully.
All right, so we have our branch edge sorted, but as traffic aggregates from the edge, it eventually hits the gateways. This is our second scenario.
Let's hear it.
The STEM reads, when designing a wireless gateway cluster in an active deployment mode, how is the client load primarily distributed among the cluster members?
And if you don't design this correctly, you end up with massive traffic jams on one gateway while the other sits completely idle.
Yeah, nobody wants that. Let's run through the distractors. Option A, the radio server assigns clients to gateways based on user roles. Option B, the access points use a round-robin algorithm to distribute individual data frames.
Right.
And option D, a dedicated external load balancer appliance intercepts and distributes the wireless traffic. Now, I want to play devil's advocate on option D for a second. We use external load balancers for web server farms all the time. Why wouldn't we use one here?
Because in this specific wireless architecture, an external load balancer is just an unnecessary extra hop. It adds a point of failure, it increases latency, and, adds hardware cost. The gateways are designed to cluster natively. Now, look at option A, the Radius server. Radius operates strictly at the authentication layer. It has zero awareness of real-time RF conditions, queue depths, or gateway CPU loads. It simply cannot perform active data plane load balancing.
What about option B? Having the access points use round-robin to send individual data frames alternating between gateways.
Oh, that is a recipe for a catastrophic network meltdown.
Wait, really? Why?
Well, think about it. If you send data frame 1 to gateway A and data frame 2 to gateway B, those frames are going to take slightly different times to process. They will arrive at the destination out of order.
Oh, I see.
Yeah, and the TCP protocol hates out-of-order packets. It will assume network congestion and throttle the client's bandwidth to an absolute crawl. You destroy session stability.
Which perfectly explains why option C is correct.
Yeah.
The access points establish connections to multiple gateways and distribute clients based on user MSE addresses. It's deterministic.
Exactly. The access point looks at the client's MSE address, runs it through a hash, and effectively pins that specific client's entire session to a specific gateway.
So all the frames go to one place.
Right, keeping the session stable while mathematically distributing the total user base evenly across the cluster.
Makes total sense. We've built the hardware logic.
Right.
Now let's talk about the human experience traversing that logic, specifically in a high-stakes environment. Here is our next question stem.
Shoot.
A hospital is deploying VoLAN, or voice over LAN, communication badges for nurses. To ensure uninterrupted voice calls while nurses move rapidly between different wards, which set of IE standards should the architect ensure is supported and enabled on both the APs and the client devices?
This is a fantastic scenario because it forces you to prioritize network characteristics. I mean, a hospital environment means roaming is a life or death requirement.
It really is. The options pull from very different protocol families. Option A, high throughput and very high throughput standards. Option C, power over Ethernet and energy efficient Ethernet standards. And option D, wireless intrusion protection and management frame protection standards. Now, my instinct always leans toward option A. Usually we want our networks to be as fast as possible. Why isn't maximum speed the priority for voice?
What's fascinating here is the physical nature of voice data. A digitized voice call requires incredibly little bandwidth, often less than 100 kilobits per second. High throughput standards like 802.1 NAC or AX just don't help.
So what does it need?
What a voice call absolutely requires is ultra-low latency.
Because if a nurse is running down a hallway, the badge has to disconnect from one access point and reconnect to the next.
Right. And in a standard secure network, that handoff requires a full 802.1x authentication exchange with the Radius server. That takes about 500 milliseconds.
Half a second.
Yeah, and for a web page, you don't even notice half a second. But for a voice call, anything over 150 milliseconds of delay causes the audio to clip or drop entirely. Speed, option A, or power efficiency, option C, or even management frame protection, option D, do absolutely nothing to eliminate that 500 millisecond delay.
So the solution has to be option B, fast BSS transition and radio resource management standards.
Precisely. Fast BSS transition, known as 802.1R, allows the wireless infrastructure to cache the client's cryptographic master keys across the mobility domain.
Oh, nice.
So when the nurse's badge roams, it doesn't have to talk to the Radius server. It just does a quick four-way handshake with the new AP. The roam happens in under 50 milliseconds, and the voice packets never skip a beat.
Okay, so the nurses are moving seamlessly. But if you have hundreds of nurses roaming constantly, dropping and connecting to APs, that network is generating thousands, maybe millions of log entries.
Oh, yeah, easily.
How does the IT admin avoid drowning in the noise? Let's look at the next STEM. A network administrator is complaining about receiving too many alerts for minor transient wireless issues. They want a solution that uses machine learning to establish a baseline of normal network behavior and only alerts on significant deviations. Which feature within Aruba Central addresses this requirement?
Alert fatigue is one of the leading causes of actual outages. When everything is an emergency, nothing is. Engineers just start ignoring the dashboard.
It's the boy who cried wolf.
Yeah.
Let's check the distractors. Option A, visual RF. Option C, unified threat management. Option D, application visibility and control. I can tell you right now, visual RF is a planning tool for mapping out the physical floor plan and heat maps. It's not an alerting engine, so A is out.
And option C, unified threat management, is a security feature. It's a firewall scanning for malware and malicious intrusions.
Right.
Option D, application visibility, is just a traffic analysis tool. It tells you if your users are eating up bandwidth on YouTube or Zoom. Neither of those utilizes machine learning to establish an operational baseline of the network's health.
Leaving us with option B, AI Insights.
Yes, AI Insights ingests all those millions of telemetry data points over time. It learns the rhythm of your specific building.
What do you mean by rhythm?
Well, it realizes that 2 a.m., it's completely normal for 50 devices to briefly disconnect during an automated backup window. It establishes that as the baseline, effectively silencing the noise so it doesn't trigger a pager alert. It only flags the anomalies that actually require human intervention.
The network is running smoothly, and the admins are actually sleeping through the night. I love it. But now we have to secure this environment against a massive invasion of devices.
Let's dive into Zero Trust architecture. Here is the STEM.
Let's do it.
To enhance visibility, a security team wants ClearPass to automatically categorize new unmanaged network devices based on their network behavior and communication patterns. Which ClearPass feature or integration provides this advanced profiling capability?
The operative word here is unmanaged. We are talking about the explosion of IoT Internet of Things. Smart thermostats, IP cameras, medical infusion pumps.
Things that don't have a traditional operating system we can control.
The options are basically a tour of the ClearPass suite. Option B, ClearPass Onboard. Option C, ClearPass Guest. Option D, ClearPass OnGuard. And Option A, ClearPass Device Insight.
Let's eliminate them based on their fundamental mechanisms. Option B, Onboard, is a provisioning tool. It generates certificates to help an employee securely connect their personal iPhone to the corporate Wi-Fi. It requires user interaction.
Okay, so that's out.
Right. Option C, Guest, is literally just a captive web portal for visitors to click I accept. And Option D, OnGuard, performs deep compliance checking, but it requires a software agent to be installed on the device.
But you can't install a software agent on a smart light bulb or a heart rate monitor.
Exactly. Which is why the answer is Option A, ClearPass Device Insight. In a world where unmanaged IoT devices vastly outnumber corporate laptops, you need behavioral fingerprinting.
Behavioral fingerprinting.
Yeah. Device Insight uses machine learning to watch the traffic. If an unknown device boots up and immediately tries to contact a known vendor server for a specific brand of security cameras using a specific port, Device Insight says, aha, based on your behavior, you are an IP camera, and categorizes it automatically so the network can apply the correct security policy.
That handles the unknown devices beautifully. But what about the devices we do know, like the corporate laptops issued to the staff? That brings us to our next STEM.
Okay.
Before allowing corporate laptops to access the internal network, the security policy requires verification that the local firewall is enabled and the antivirus definitions are up to date. Which ClearPass module is designed specifically to perform this endpoint posture assessment?
Now we are on the other side of the coin. We are dealing with robust operating systems that can run agents.
Let's review the options. Option A, ClearPass Guest. Option B, ClearPass Policy Manager Core. Option C, ClearPass Onboard. Option D, ClearPass OnGuard. We just established that Guest and Onboard are for web portals and certificate provisioning.
Yeah.
And Policy Manager Core is just the central brain that makes the final radius decision. It doesn't actually scan the laptop itself.
Right. So the correct answer is Option D, ClearPass OnGuard.
You know, I used to think of OnGuard as a bouncer at a club, but it's really more like a health inspector at a restaurant.
Oh, I like that.
Yeah, before the restaurant is allowed to open its doors to the public, or in this case, access the network, the inspector comes in. They check if the kitchen is clean, which means verifying the firewall is turned on. They check if the ingredients are fresh, verifying the antivirus signatures are updated from today.
I love that analogy. If the laptop fails the health inspection, OnGuard denies the permit. It can throw the laptop into a quarantine VLAN with restricted access just to download the necessary security patches, completely protecting the rest of the network from a potentially compromised machine.
So, laptops get the health inspector. But let's go back to those vulnerable, dumb IoT devices, specifically the ones plugged into the wall. Here is a complex scenario.
Let's hear the stem.
An organization wants to implement user-based tunneling for wired IoT devices.
Yeah.
They need to ensure that traffic from these devices is securely isolated and inspected by a centralized firewall. Which combination of Aruba solutions is necessary to achieve this design?
This is a high-level architectural challenge because you are taking advanced security concepts usually reserved for wireless roaming and, well, forcing them onto the physical wired ports of a switch.
Let's look at the combinations offered. Option A, mobility conductors and airwave management. Option B, AOS switch operating in standalone mode and central. Option D, Aruba instant APs and a third-party radio server.
Let's dismantle these. Option A gives you network management orchestration, but it completely lacks the policy enforcement engine required to actually evaluate the devices.
Right, no enforcer.
Exactly. Option B suggests standalone switches. Unfortunately, standalone modes often lack the dynamic, real-time tunneling capabilities required to encapsulate the traffic. Option D relies on instant APs, which manage wireless traffic, not the physical wired ports mentioned in the prompt.
Which leaves us with the correct answer. Option C, AOS-CX switches, ClearPass Policy Manager, and Aruba gateways.
If we connect this to the bigger picture, this is the triad required for user-based tunneling. It's a synchronized dance. First, the AOS-CX switch acts as the physical connection point and authenticates the port.
Okay, step one.
Second, ClearPass acts as the intelligence, profiling the IoT device and sending down a user role. Third, based on that role, the CX switch builds a dynamic tunnel directly to the Aruba gateway. The gateway acts as the enforcer, receiving that tunnel traffic and running it through a deep packet inspection firewall before it ever touches the rest of the network. You absolutely need all three components.
Okay, we've secured the edge, we've handled the roaming, we've locked down both known and unknown devices. But all this edge traffic, all these tunnels, ultimately funnel into the heavy machinery, the campus core. Let's examine our next stem.
We're getting into the weeds now.
An enterprise is moving towards a micro-segmented campus network architecture. They want to extend Layer 2 domains across a Layer 3 underlay network while maintaining strict isolation between different tenant networks. Which protocol suite is most appropriate for this data plane and control plane design?
This is where we leave the edge behind and get into the heavy lifting of modern core infrastructure.
And the options are a massive alphabet soup of protocols. Option A, OSPF and PIM sparse mode. Option B, BGP and multi-protocol label switching, or MPLS. Option D, RIPv2 and generic routing encapsulation, GRE. Why wouldn't we use BGP and MPLS? Option B. Service providers use it to isolate customer traffic all the time.
They do, but an enterprise campus is not a global service provider. MPLS is incredibly rigid. It requires complex label distribution protocols and extensive manual engineering that just doesn't scale well in a highly dynamic, localized campus where users are constantly moving.
So it's overkill.
Exactly. And option D, RIPv2 and GRE. RIP is an ancient distance vector routing protocol that makes decisions based on hop count. It is completely unsuitable for a modern high-speed core.
What about option A?
Option A suggests OSPF and PIM. OSPF is great for routing, but PIM is protocol-independent multicast. It's used for streaming video to multiple endpoints, not for extending Layer 2 VLANs.
So we arrive at option C, EVPN and VXLAN.
Exactly. Let's break down the mechanisms. Traditional VLANs are limited to 4096 tags, and they rely on spanning tree protocol, which blocks redundant links. VXLAN solves this.
So.
It acts as the data plane, taking the original Layer 2 Ethernet frame and encapsulating it inside a standard Layer 3 UDP packet. You can route it anywhere across the core. But to prevent the network from flooding broadcast traffic everywhere to find MAC addresses, we need a control plane.
Which is where EVPN comes in.
You got it. That is EVPN. EVPN uses BGP to intelligently advertise MAC addresses like routing updates. Together, EVPN and VXLAN give you infinite scalability and strict tenant isolation without the legacy baggage of spanning tree.
Now, speaking of the core routing, those routing tables can get dangerously bloated in massive campuses. Here is the stem addressing that. A large campus network is divided into multiple buildings. The core switches act as the OSPF backbone area. To minimize the routing table size on the building aggregation switches and reduce the impact of link flaps within the buildings, how should the architect design the OSPF areas?
Route optimization is all about hiding unnecessary information to protect the CPU of your switches.
Let me push back on this, looking at the distractors. Option A says, place all building switches in the backbone area. Why wouldn't we just make every single switch part of Area 0 so every switch has a complete map of the entire network?
Because of the Dijkstra algorithm, in OSPF, every time a physical link goes up or down a link flap, the router generates a link state advertisement. If everyone is in Area 0, that advertisement is flooded to every single switch in the campus.
Sounds noisy.
Very. Every switch then has to dump its routing table, run a complex mathematical algorithm on its CPU, and recalculate the shortest path. If a bad cable in Building 3 is flapping 50 times a minute, you create an SPF calculation storm that spikes the CPUs of every core switch to 100%, causing a massive campus-wide outage.
Okay, valid point. Let's avoid the massive outage. What about option B? Configure the building aggregation switches as autonomous system boundary routers, or ASBRs, or option C, use virtual links to connect the access layer switches directly to the backbone.
Well, ASBRs, option B, are specifically used for taking routes from a completely different protocol like BGP and injecting them into OSPF. That increases complexity. It doesn't simplify the table.
And option C.
Virtual links are basically duct tape. They're a band-aid for broken network designs where an OSPF area doesn't physically touch the backbone. It's a temporary fix, not a proactive architectural strategy.
So the elegant solution is option D. Configure each building as a totally stubby area.
Yes. A totally stubby area places a boundary at the building's edge. It tells the internal building switches you do not need to know the specific granular path to every single subnet in the rest of the world. If you need to send traffic outside your building, just hand it to the core switch.
That's a lot simpler.
Much simpler. It blocks those flapping link state advertisements from entering and replaces thousands of specific routes with a single default route. You shrink the routing table and protect the core.
Brilliant. Now, for our final scenario. If the core goes down, the whole company stops. How do we upgrade the software on the core without anyone noticing? The stem reads, when designing a campus core using AOS-CX switches, a customer requires continuous layer 2 forwarding during a control plane software upgrade. Which technology should the architect recommend?
Pitless upgrades. This is the holy grail of network maintenance. No more 3.00 AM maintenance windows taking the factory offline.
We have 4 options. Option A, virtual switching framework. Option C, multiple spanning tree protocol. Option D, open shortest path first graceful restart.
Option C, MSTP, is a loop prevention mechanism, not a software upgrade tool. Option D, OSPF graceful restart, allows a router to reboot its control plane while neighbors hold its layer 3 routes. But the prompt specifically asked for continuous layer 2 forwarding.
That leaves option A, virtual switching framework, or VSF, and option B, virtual switching extension, or VSX. They sound almost identical to the uninitiated.
They sound similar, but their internal architecture is vastly different. VSF is an older stacking technology. It physically combines 2 switches into one logical switch.
Which sounds good.
Except for the critical flaw, they share a single synchronized control plane. If you have to reboot that control plane to load a new software image, both switches go down temporarily. Traffic drops. It is not hitless.
But option B, virtual switching extension.
VSX is designed for high availability. It allows 2 independent switches to operate as a pair, but they maintain entirely separate independent control planes. The data planes are linked, but the brains are separate.
So you can upgrade one at a time.
Exactly. You can trigger an upgrade on switch 1, it reboots its control plane, and switch 2 seamlessly takes over 100% of the layer 2 forwarding without dropping a single frame. Once switch 1 is back online, you upgrade switch 2, hitless, 0 downtime.
Thanks for joining us on this deep dive. Keep studying, trust your logic, and we'll see you next time.